Okay, this is 3.4b. So, and I'm going to type this. A line of best fit is a straight line drawn through data points to best represent a linear means line, by the way, linear relationship between two variables, okay? So it's not just one variable, it's two variables, aka a trend line or regression line. So note, the weaker the correlation, the more difficult it is to actually draw that line of best fit, okay? Just because the line of best fit is going to probably not be representative, and a lot of the points are going to be away from the line of best fit, so you're going to be like debating in your head. Okay, the effective outliers on the line of best fit. An outlier is a point that lies like really far away from the main cluster of data. It may be caused by inaccurate measurements or anomalies in the data set. So like an unusually tall person or an unusually short person type of idea, if you're talking about height. The line of best fit should reflect all points in the data set, including outliers. Okay? So for the purpose of the rest of this note, let's include outliers. We can talk about deleting them depending on how far away they are. Okay? One or more outliers will affect the path of the line of best fit. So for right now, leave them in, and then if the question says to take them out, then ignore them. Okay? So analyze each graph below to determine if the line shown is the line of best fit for the data. Okay, so I'm going to say for graph A, if we take a look at this line, most of the points are above and below it. What this line actually gets rid of are these two outliers. Okay, so yes, directly through, so this line, right in full sentences, this line is directly through the data. However, it disregards the outliers. Okay, so it is representative, but it does disregard the outliers. Okay, graph B is the same amount of points, are the same amount of points on top of the line of best fit as beneath them? No, absolutely not. These two outliers are really pulling that line down. I don't think that this is representative. So no, the line of best fit is not near the majority. I'm going to put that in capitals of the data. Okay, you have to be near and like going through the majority of the data. Also, the same number of data points are not on either side of the line of best fit. Okay, and graph C. I'm going to say yes. This is the best line of best fit when considering the outliers. Okay, if you take a look, it goes through data points. Okay, the line of best fit goes through data points, and the same amount of points are on either side of the line. Okay, now interpolating and extrapolating, a line of best fit can be used to interpolate, okay, or extrapolate values. And then estimating values that lie among known values on the graph is called interpolation. Okay, and then predicting values that lie beyond known values is extrapolation. Deciding if a correlation is linear. So not all relationships between two variables will be linear. Okay? A linear model may be unreliable if, so these are some of the criteria. There's too few data pieces of data, so it's a small sample size. Okay, you can't just collect data on like one or two and then umbrella the rest under like those two examples, right? That would be extreme. The range of the data is too narrow. There does not appear to be any correlation, or the data do not appear to be linear. So this would just be like the shape of the graph, right? This would just be looking at it. Or if there are outliers, okay, that may be unreliable too. Okay, example 2A. Below are pre-exam term marks and exam marks for some students in a grade 12 math class. Okay, so here they are. So whenever we have a chart, the first or like the left-hand side or the top one is going to be the X, and this is going to be the Y. So we're going to graph the data and draw the line of best fit. So again, X, Y, we're going to label term mark, and this is measured in percentages, and exam mark, and this is also measured in percentages. Okay, so let's graph again in green. Okay, and the graph goes from 0 to 100 on both the axes, and this is probably because percentages don't go above 100, so it's safe. Okay, 84, 80. So 84, 80, 76, 72, 70, 68, 95, 96. Those 92, 90, 61, 58, 25, 29, 55, 60, 51, 53, 73, 77, and then 62, 67. Okay, here we go. Let's draw the line of best fit. I'm going to say that it goes, and it doesn't have to be perfect. There we go. Okay, just make sure that you draw it with the line with a ruler, and then you extend it just in case we have to interpolate or extrapolate. Okay, so in this one it's going to be a little bit different. We're going to use algebra instead of just locating it on the graph. So we're going to recall the slope and then the equation of a line. So there's 3 steps in finding the equation of our line of best fit. Number 1 is to find the slope. Okay, so we're going to use as like a review, y2 minus y1. That just means that we're going to find the difference in the y's, and then x2 minus x1, the difference in the x's. So if we take a look, we want to kind of locate 2 points that our line goes through. It usually goes through 2 points. If not, maybe you can revisit your line of best fit and the 2 closest points. Okay, so I have these 2 points right here, and this point here is 25, 29, and then this point up here is 73, 77. Okay, so this is 25, and then this number is going to be 73. So what we're trying to do is we're trying to find the difference between those numbers. So that would be the difference in the x, which is 73 minus 25. okay? And then the difference in the y's, if you locate this one is 29. And then if we go to this y here, this is our 77 here. So we then want to find the difference in the y's, okay? So we're going to do 77 minus 29, okay? So if you were to calculate this, what we're going to get is we're going to get 48 over 48. That doesn't happen all the time. Don't think that at all. But it just does for this case, which is fine, okay? So that's step one. Now back to blue, okay? So let's go step two. Find the y-intercept. So we have to find the y-intercept, which is b in this equation. Y equals mx plus b. So here's the thing. We know what m is. M is 1. So let's sub that in, okay? We also have 2 points. We have the point 25, 29, and 73, 77. So pick either of these 2 points. Let's pick 25, 29, just because it's smaller. Okay, and we're going to sub in 29 equals 1. Also sub in that x, 25 plus b. Okay, what's 1 times 25? Well, that's 25. And this 25 we have to bring over. And what we want to do when we bring this over, we want to subtract the 25. Okay, so I get b equals 4. So my equation, I get y equals 1x plus 4. That is the equation of this line. So I can come back up here and label y equals x plus 4. Okay, now what we can do is we can actually use this line to solve for C and D. So there's a typo here. Use the graph. Oh, sorry. Use the graph to estimate the exam mark of a student with a term mark of 80. No, we're good. Okay, so we want to estimate the exam mark. So let's look up term mark of 80. And let's go all the way up to the line of best fit. Okay, let's start with the line of best fit and let's go over. I'm going to say it's approximately 81. Okay, so if we use the graph, we're going to get 81 on the graph. Now D says use the equation. Okay, so it's different. Graph versus equation. So we're still going to predict the exam mark, and the exam mark is our y, and it gives us the term mark, which is x, is 80. So let's write out y equals 1x plus 4, and let's sub in x equals 80. So 1 times 80 plus 4, which is just 80 plus 4. So I get y equals 84%. Okay, so looking at the graph gave us 81, but actually solving for a line of best fit gave us 84. Depending on what you're asked, both of these are correct if you're asked to use the graph or to use the equation, respectively. For example 2b, we're actually going to deal with the exact same data set as in 2a. And we're going to repeat the process of making a scatter plot and finding the line of best fit of the data. But now what we're going to do is we're going to just use graphing software. So I'm just going to use Excel. Most of us have this through school on the cloud, so it's accessible. Okay, and then let's compare our values after, compare our results. So step 1, enter the data in 2 columns in the Excel spreadsheet. It's going to look like this. I'm going to go ahead and do that. Highlight the data to create a scatter plot. As soon as we highlight the data, you're going to go to this button here and just like the scatter plot option, so nothing connected. And then step 3, after you click on the scatter plot and it's highlighted, what we can do is we can actually change the way it looks by going quick layout. I choose this one, because it has the trend line with the equation. So then what we can do is we can take that equation and compare it to the equation that we got. Okay, so let me walk everyone through that right now, and you'll see how quickly, this is step 2, this is step 3, how quickly you can actually get through this. Excel's very, very user-friendly. Okay, so I'm going to write term mark, and I'm going to write exam mark. Okay, and I'm just going to go down here. 84, enter. 76, enter. 70, 95, 92, 60, and I'm just pressing enter after each data point here. And you might want to mimic this just to see if you can like get through this question and get the same answer as me. Oops, 67. Okay, so that's step 1 done. Okay, pretty easy. Step 2, what we're going to do is we're going to highlight. We're going to highlight our data. You have to highlight both of the columns. Okay, and I'm going to put insert, and it's the drop down menu for me. When you have your Excel on like your entire page, this bar is going to look a little bit different because it's going to be blown up and it's going to give you more options, but it's this drop down menu and just the scatter plot. Okay, done. Already made the scatter plot. Now I'm going to click on the scatter plot. So the scatter plot is actually highlighted right now, right? So let's move this over. Okay, so it's highlighted right now, and what you can do from here is you can go into chart design, quick layout. So I choose the one, it's layout 9, and it lists exactly what you're going to have. What I basically look for is that I can change this axis title. So this axis title is going to be the term mark, and then that's measured in percentage. And then this axis title is going to be exam mark, and again, that's measured in percentages. This is going to be, if we look back, it's going to be grade 12 math marks. Grade 12 math marks. That's fine. Okay. This right here is kind of what we're looking for. So we get for these values, this is the line of best fit, and then we're going to compare in just a second. Okay, so what we have here, I'm going to write it y equals 0.9063x plus 6.8804. I'm just gonna round to two decimals. Okay, so here we go. Let's actually compare these values, okay? So manually we got 1x plus 4, software we got 0.91x plus almost 7, right? 6.9. So are these quite similar? I think that they're quite similar. What wouldn't be similar is like 1 and like 0.7. Like that would be very, very much off. But these, like the slopes are very much the same. What we did here for the manual, so let's just talk about the manual, okay? The one that we did by hand. We put the slope too much up. So our line of best fit is, let's go, increases faster. Is increasing faster. Okay, and then you want to comment, so that has to do with the slope, which is m. Now let's comment on b, which is our y-intercept. Okay, so again, let's just talk about the manual. Our y-intercept is lower. Okay, so now let's just take a look at the bottom here. The r squared is called the coefficient of determination. Basically, what r squared does is it tells you how closely fit the line is around the data. So how, like, it tells us the percentage of change in one variable in like dependent on the other. So formally, changes in the dependent variable, what percentage of those are due to the change of the independent variable. We call this the correlation or the relationship. Okay, this value is between 0 and 1, and the reason why it's going to be like positive is because what we do is we take that r squared and we root it to get r. Okay, the closer to 1, the stronger the relationship. 1 would be a line, like a perfect line. Okay, so on our graph, let's just take a look here. On our graph, we get r squared equals 0.9716. Okay, so our r squared is 0.9716. Okay, now the r is what we're really actually interested in. So the r is called the correlation coefficient. What we do is we take the r squared and we end up rooting both sides. So this root and this squared go away, and we're left with, for this one, root 0.9716. I get 9856. I'm going to round up to almost 99. Okay, so 0.99. Okay, the fact that 1 or -1, this is positive, but the fact that 1 and -1 are perfect lines, this is like the closest that you can get to 1 when it's rounded. So we're pretty close to a perfect line. The further you get away from 1, like the further you go down to 0, the less of a line it's going to look like. So if we read this, this is called the correlation coefficient. The correlation coefficient gives the measure of the strength, okay, of the linear correlation between the two variables. In other words, it indicates how closely the data points cluster around the line of best fit. So very, very similar. This value ranges in values between -1 and 1. Okay. When r equals 1, it's perfect linear. Okay, so it's a perfect line. Or -1, it's a perfect line as well. But positive goes up, negative goes down. So if we were to put this into like one of these, negative correlation or positive correlation, it would land right here. It's positive 0.99. So how we would classify this is we would say that there's a positive, let me change colors, okay? We would say that there's positive, strong correlation. Positive, strong correlation. So let's just take a look at this data and like these different graphs. So r equals 1. So this is a perfect linear correlation. All of the points are in a line. Okay. Because this is a positive number, there's a positive slope. It goes up to the right. Every point lies exactly on the line of best fit. Okay. Remember, this could be positive or it could be negative. It could be going down. Now, r equals negative 0.92. So negative means it goes down to the right. And then the 0.92 means it's pretty close to the line. Most of the points cluster around the line, but the points are clustered tightly, but not perfectly. Okay, so this line going up, we can see from the line that this is going to be positive. Now when we look over here, yeah, r is positive. That means there's a positive slope. This is moderate because the points are clustered somewhat tightly around the line of best fit, but not too tight. So it's getting a little bit more sparse there. So we call that moderate. Okay, weak linear correlation. Okay, so this negative sign means that it's going down to the right, so it's negative slope. And if you see, the points are somewhat clustered around the line with a slight trend. Okay, no correlation is going to be one of two things. It's either going to be dots everywhere and you can't find a trend. Remember how we were talking about how the weaker the trend, the more difficult it is to draw the line of best fit? Well, it's very difficult to draw a line of best fit in that. There's no correlation. As x changes, y doesn't seem to change with the x, it's just random. Okay, the other one is when it's a horizontal line. So if it's a horizontal line of best fit, as x changes, y does not change. Y just keeps going. So what is the equation of the line of best fit in Excel? This is where we're formally going to write it. Okay, and how does this compare to yours? Is it similar, drastically different? Are the slopes both positive or both negative? Okay, so the line of best fit, I remember manually, is y equals 1x plus 4. In Excel, it was like y equals 0.92x plus 6.9. I'm going to double check. 9.1. Sorry, this is a 1. That's fine. Okay, so let's list. Both positive, similar numbers. If you think about it, like 4 and 6.9, those are similar on our scales. Our scales are to 100, right? So if you looked at our scale, it goes to 100 and 100. So like the mark of 4 and the mark of 7, rounding 7, not very far off. So both positive, similar numbers. Let's go both positive m, which is slope. Similar numbers for the y-intercept, which is the b. Okay, interpret what the line of best fit measures. Okay, so the line of best fit measures the change in the exam mark based on the change in the term mark. Okay. Now, use the graph to estimate the exam mark of a student with the term mark of 80. How does this compare? So what two answers did we get? I believe for the Excel graph we got, oh, and then manual. Okay, so for the manual graph, we got 80. So if I can recall, the manual graph, I believe we got 80. It was 80 or 81. And then the exam mark Excel graph. So actually pulling up this Excel graph, and let's blow it up a little bit more. Let's look at where 80 lies. Okay, so 80 lies here. We got to follow it up with our finger. It actually is like 80 and 80. So it's approximately the same. Okay, how does this compare? Right, so we can say we got the same thing. Now use the equation to predict the exam mark of a student with 80. And how does this compare to the original graph? Or the original, we should say equation. Right? The manual equation gave us 84, but if we were to go over here and do y equals 0.92 and sub that 80 in, sub it into the Excel equation, we get 80.5. Okay, we're going to get a little bit different than this only because we did round, but this is a little different, very close, but still off a little bit. Okay, and then looking at the Excel graph, do you see any outliers? I don't. No outliers. Okay, so we have no outliers because nothing lies up here, nothing lies down there. Everything's pretty much clustered around the graph. It is tight. It's it's going to be strong, right? Because we already found the R, but it's going to be strong and it's going to be positive. Okay, example 3, the table below was posted in a fitness club and shows the estimated maximum possible heart rate during intense physical exercise or activity based on a person's age. So this is going to be our X, this is going to be our Y. So our X here is age in years, right? How many years old someone is. And then our Y is going to be the max heart rate. And this is measured in beats per minute. Okay, so plot the graph below and draw the line of best fit through the data. So we have 10 and then 210, 20 and 200, 30 and 190, 40 and 180, 50 and 170, 60 and 160, 70 and 150, 80 and 140. Okay, so if we were to draw the line of best fit, it'd go like that. Now, solve for the line of best fit using the three steps above. So, first step is to find the slope. Let's pick 2 points on the line of best fit. Let's go 10, 210. This one here. And then let's go down to 40, 180. Okay, so what we're looking for is we're looking for the difference between this, which is 10, and 40. So we're going to go, let's do this as our first point. This is 40, 80. Okay, so we're going to go 40 minus 10, and that's going to be in the bottom. 40 minus 10. And then the rise here is going to be 210 to 180, right? But we're going to start with this point here. So 180 minus 210. So what we get here is negative 30 over 30, which we get negative 1. Okay, step 2 is finding the y-intercept. So let's go y equals mx plus b, a little darker. Okay, we're going to sub in that negative 1. And then we're going to sub in one of the points. Let's use this point here. So 210 equals negative 1, 10 plus b. So 210 equals negative 10 plus b. When we move that negative 10 over, it becomes positive 10. So I get 220 equals b. So we have m equals negative 1, b equals 220. We get y equals negative 1x plus 220. That is the equation of this line. Come back up here, y equals negative x plus 220, or negative 1x. Now C wants us to enter this data into the Excel spreadsheet and create a scatter plot and the line of best fit as well. So open up a new document on Excel. We're going to go age in years, okay, and let's go max heart rate beats per minute. Okay, so I'm not going to write this horizontally. I'm actually going to flip this and write it vertically. So I'm just going to go across, and we're going to go 10, 20, 30, 40, 50, 60, 70, 80. And that's going to be the age. Now, max heart rate, I'm not going to go that fast. 210, 200, 190, 180, 170, 160, 150, and 140. Okay, we're going to highlight that again, insert the chart, which is a scatter plot. Move this over. The graph is highlighted. Now we're going to change the layout. Now on this graph, we still want to heart rate. We want to change the axis titles. and the main title, heart rate based on physical activity. Okay, this is going to be age, and that's measured in years. And then this is going to be heart rate, and that's measured in beats per minute. We can move that, and then this is the line of best fit. So what do we notice with the line of best fit? Y equals negative x plus 220, and then we have r squared equals 1. So this, I think we got the same slope for this, -1, and let's take a look. Yeah, and then we got 220, positive 220 for like the y-intercept. When we root r squared, we root 1, and I'm going to do this on the paper. We also get 1, which means it's a perfect line. And if you take a look at this, it is a perfect line. We can also tell that it's a perfect line because going up in the x values is consistent, and then going up in the y values is also consistent. Okay, so down here, what is the r value? So r squared equals 1, and then when we root that, r also equals 1, right? Because r squared equals 1, root both sides, r equals 1. And then classify this as strong, moderate, weak, or no correlation. So our r is actually going to be negative because we're descending, we're going down. So this is strong. It's actually not even strong. This is perfect. Perfect linear, which you rarely get in real life. And then this is negative because you're going down. So it's a perfect negative correlation. We can write that down.